Sections 3.2, A.2, and A.5, polynomial division and the real zeros of polynomial functions. Polynomial long division is relevant because long division of polynomials will always work if we're trying to divide polynomials. Now, just like long division, 10 divided by 4 could be written as 10 with the symbol division by 4, or 4 into 10, just the way you want to look at it. But just to remind ourselves of the process, 4 goes into 10 how many times? Specifically, it goes twice. Then what do? We take that 2 and multiply it times 4. 2 times 4 gives us 8. Then we have a subtraction step. 10 minus 8 leaves us with 2. Then what do we do with the rest of it? We have the quotient and we have the remainder. Now, we could rewrite 10 divided by 4 as 2 with a remainder of 2/4. That's one way to write it. Of course, this will reduce as 2 plus 1/2, and you could use the mixed number notation. But something to also remember is that sometimes they won't want it written like this. We'll just want the remainder. So just pay attention to what the quotient. So now we're just going to find the quotient and the remainder. And we're going to do this by taking 3x cubed plus 4x squared plus x plus 7 divided by x squared plus 1. So polynomial long division. This is x squared plus 1 goes into 3x cubed plus 4x squared plus x plus 7. When dealing with polynomial division, make sure that you have every term of decreasing degree from the highest degree. So this is a degree 3 term, so we need 2, 1, and 0, so we're good. So now for our polynomial division. What you're doing is x squared times what number will give us 3x cubed? The answer here is 3x. Then we have a multiply stage. So we multiply. 3x times x squared gives us 3x cubed. 3x times 1 is 3x. But notice that that doesn't do anything with this x squared stuff, so we need to put it where it belongs, which is over here, plus 3x. Now, what was the next part of our process in long division? Well, it's the subtraction stage. So we need to subtract this binomial that we've just gotten from multiplication. So you can distribute the negative. That's going to be plus, minus, minus. So that is 3x cubed minus 3x cubed is 0. And x minus 3x is negative 2x. Then we should bring down everything that's left over. So this is going to be plus 4x squared plus 7. Now we just repeat the process. What number times x squared will give us 4x squared? Well, x squared and x squared are the same, so we're not going to multiply times any x's. But 4 times x squared will give us 4x squared, so I'm going to multiply by 4. Then the multiplication stage. 4 times x squared is 4x squared. 4 times 1 is positive 4. Then we have the subtraction stage. That is minus all of this, so I can distribute that negative. That's minus 4x squared minus 4. So 4x squared minus 4x squared is 0. We're left over with negative 2x. 7 minus 4 is positive 3. So I get negative 2x plus 3. So to identify the two things, the quotient and the remainder, the quotient is this stuff up top, 3x plus 4. The remainder is just whatever we're left over. When I say left over, we do have to check to make sure we're done with our polynomial division. And that is, whatever's down here has to have a degree less than the divisor. And so the degree of the divisor is squared, so it's 2, second degree. The degree down here currently is 1. That's how we knew to stop. And so our remainder is negative 2x plus 3. Same process. So we're dividing by x. We're dividing 2x cubed minus 7x squared plus 1 divided by x plus 7. So that is x plus 7 into 2x cubed minus 7x squared. Now I noticed something. I started with x cubed, so I got to have x squared. I also need x to the first, but notice that there isn't one. So I need to add a placeholder. My placeholder is just going to be 0 times x. Then next decreasing order of degree is a 0 degree term, but that's just the constant. That's 1. So now we're set up and ready to go. So then, first step, what number times x will give us 2x cubed? Well, that answer is 2x squared. Step 2, multiply. 2x squared times x is 2x x cubed. 2x squared times 7 is positive 14x squared. Next step, subtraction stage. So we subtract. I'm going to distribute that negative. That's plus, minus, minus. 2x cubed minus 2x cubed is 0. Negative 7x squared minus 14x squared is negative 21x squared. Then we can bring down the rest of it. Plus 0x plus 1. Then we start over. What number times x will give us negative 21x squared? Well, that's going to be negative 21x. So now we multiply. Negative 21x times x is negative 21x squared. Negative 21x times 7 is negative 147x. So then we have the subtraction stage. So we subtract all of this, distribute that negative. Then negative 21x squared plus 21x squared should give us 0. It does. Plus 0x plus 147x is plus 147x. Bring down what's left over, plus 1. Next question. Let's check to see if we're done yet. Check the degree down here. This is a degree 1 polynomial. This is degree 1. We're not less. We can keep going. What number times x gives me 147x? That is 147. Multiplication stage, 147 times x is positive 147x. 147 times 7 is plus 1029. Then next stage is subtraction. Distribute that negative. That is 147x minus 147x, that's 0. Positive 1 minus 1029, that's going to be negative 1028. Then notice that this is a degree 0 term. This is degree 1. We are finished. Thus, our quotient is 2x squared minus 21x plus 147. And the remainder is negative 1028. Synthetic division is an abbreviated version of long division. Problem with synthetic division is it only works when dividing by a linear factor. Not only does it have to be a linear factor, but the leading coefficient should be 1. There's a way to manipulate it to make it work, but it gets a little tricky. Then our quotient is just going to be reduced by 1 degree from whatever our original polynomial was. And the way we're going to set this up, it's going to look like this. We're going to put the roots or the zeros here, and the coefficient of the polynomials here. Now when I say roots, we're going to do this one at a time. So we're going to use synthetic division to find the quotient and remainder of these two things. First off, if we're dividing by x plus 7, we do have to double check to make sure it's linear. It's degree 1 polynomial, it's linear. The leading coefficient is 1, so nothing weird has to happen. So now we just need to find the zeros. Well, the 0 is x plus 7 is equal to 0, minus 7 minus 7, x is equal to negative 7. So our 0 is negative 7. So when we do this synthetic division, it's going to look like this. The 0, which we now have, is negative 7. Then we're going to write coefficients here. So the coefficients are 2. We do have to make sure we have every decreasing order of degree. So 3, 2, 1, 0, we're fine. So 2, negative 7, positive 2, positive 1, those are our coefficients. Synthetic division works like this. Bring down the leading coefficient. It's 2. Then take your 0, multiply it times 2. Negative 7 times 2 is negative 14. And then we add straight down. Negative 7 minus 14 is negative 21. Then repeat. Negative 7 times negative 21, that's going to give us 147. And then add down. 2 plus 147 is 149. Then negative 7 times 149 is going to be negative 1043. Then add down. That's going to be negative 1042. Now, what happened? At this point, we have found all of the division. We have a quotient and a remainder. Now, we can't leave them like this. We have to actually write them correctly. And so notice that this was a degree 3 polynomial that we were dividing into. And so that is, this will be 1 degree less. So this is going to be 2x squared minus 21 times x plus 149. This is my quotient. The remainder is just negative 1042, negative 1042, and we found our remainder. And this is what synthetic division is good for. It's for working very quickly. But once again, it only works if our divisor is linear. So now let's use synthetic division to find the quotient and the remainder when x to the 5th plus 32 is divided by x plus 2. First, we need to find our 0 of the divisor. 0 is x plus 2 is equal to 0, minus 2 minus 2, x is equal to negative 2. So then I've got negative 2, and then I can deal with my coefficients. Notice that I have x to the 5th. I'm missing 4th, 3rd, 2nd, and 1st because this is the 0 degree, so I've got to have a bunch of placeholders. So let's double check ourselves. The leading coefficient is 1. Then the 4th degree term coefficient is 0. 3rd degree coefficient is 0. 2nd degree coefficient is 0. 1st degree coefficient is 0. And 32 is the constant, so 32 comes over here by itself. Then synthetic division, bring down that leading coefficient, that's 1. Then multiply, negative 2 times 1 is negative 2. Add down, that gives me negative 2. Multiply, that's positive 4. Add down, that's 4. Multiply, that's negative 8. Add down, that's negative 8. Multiply, that's positive 16. Add down, that's 16. Multiply, that's negative 32. Add down, I get 0. Now at this point we have a remainder of 0. What this means is that technically x to the 5th plus 32 divides nicely by x plus 2. And what does it give us? It gives us a quotient of, this is x to the 5th, so this is x to the 4th. So x to the 4th minus 2x cubed plus 4x squared minus 8x plus the constant 16. So that is what our division gives us. And the remainder here is 0. There is no remainder. It divides nicely. The remainder theorem is an interesting property of polynomials. That is, if we know that x is some value c, and you want to know what is the polynomial when it takes in c. The answer is actually the remainder. Also notice that if p of c is equal to 0, then x minus c is a factor of the polynomial. So the factor theorem is really something we've already stated. That is, x minus c is a factor of p of x if and only if p of c is equal to 0. For this example, we're going to use the remainder theorem to find the remainder of this function f of x when it's divided by x plus 3. But real quick, this is really easy because the remainder theorem just says, oh, take f, plug in the 0 of your divisor, so the 0 of x plus 3 is negative 3. Whatever you get is the remainder. This is the remainder. So f of negative 3 is going to be 3 times negative 3 to the 6th plus 89 times negative 3 to the 3rd plus 216. I claim that this will give us 2,187 minus 2,403 plus 216, and then that's going to give me 0. So specifically, that means that x plus 3 is a factor of 3x to the 6th plus 89x cubed plus 216. Then the factor theorem uses what we just found, that is, f of negative 3 being equal to 0, allows us to say, oh, I know that that means that x plus 3 is a factor of our function f of x. So let's try this again. We're going to use the remainder theorem to find the remainder. Given 3x to the 6th minus 27x to the 4th plus x cubed minus 20 is divided by x plus 3. So find our 0 here. Our 0 is negative 3. F of negative 3, that's going to be 3 times negative 3 to the 6th minus 27 negative 3 to the 4th plus negative 3 cubed minus 20. I believe this gives us 2,187 minus 2,187 minus 27 minus 20, and that's going to give us negative 47. So now I know that my remainder, if I divide f of x by x plus 3, I'm going to get a remainder of negative 47. Well, then the factor theorem, what does the factor theorem tell us? Well, the factor theorem tells us that since f of negative 3 is not equal to 0, then x plus 3 is not a factor of our function. The rational zeros theorem lets us use what we know about a polynomial and try to find possible zeros of that polynomial. Specifically, if we look at the coefficient, the leading coefficient, and then the constant term. If you take the factors of the constant term and divide them by the factors of the leading coefficient, the list that you create will be a list of possible rational zeros for any polynomial. Doesn't mean all of them will be there, but it does mean that every rational zero will be in that list. So we're going to do that. We're going to list the potential rational zeros of this polynomial function. So first off, to do that, we need to look at the leading term and the constant. We need to write out its factors. So 2 has factors of 1 and 2. 1 times 2 are the only numbers multiplied together that give us 2. 2 is prime. The factors of 10 are 1 and 10, 2 and 5. There are no other factors. So now when we make our list of rational zeros, what this is going to look like is just fraction form, but you could have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Each one of those numbers divided by factors of the leading coefficient, which are plus or minus 1, plus or minus 2. And so that means that if I'm trying to write these out, that's going to give me the list of plus and minus 1 over 1 or 1, plus and minus 1 over 2, plus and minus 2 over 1 or 2, plus and minus 2 over 2, which is 1, but since we've already written it, we're not going to write it again, plus and minus 5 over 1, which is 5, plus and minus 5 over 2, then plus or minus 10 over 1, which is 10, and plus or minus 10 over 2, but that's really plus or minus 5, so we're not going to rewrite it. So my claim here is that this is a list of possible zeros of this function. It doesn't mean every one of them is a zero, but it does mean that if we have any rational zeros, they will come from this list. And remember, rationals are our whole numbers. They're also our fractions. So our steps for finding real zeros of a polynomial function. First, determine all the possible rational zeros. Make that list like we just did. Then use synthetic division until you get to a quadratic function. So essentially just keep using those rational zeros in synthetic division, and anytime you get a remainder of 0, you know that that thing is a 0, then you get a factor. Then you can solve the quadratic or factor the quadratic, and we're done. So let's say we want to find all the real solutions of 5x cubed plus 8x squared minus 9x plus 2. So first off, let's make our list of possible rational zeros. So remember that that's going to be the factors of the constant term over the factors of the leading coefficient. The factors of the constant term are 2 times 1, and the factors of the leading coefficient are 5 times 1. We have a really short list here. This is going to be very pleasant. So then our list of possible rational zeros are, once again, factors of the constant over factors of the leading coefficient. So that's going to be 1 over 1, or plus or minus 1. 1 over 5, so plus or minus 1/5. 2 over 1, so that's plus or minus 2. And 2 over 5, plus or minus 2/5. Once again, this is a possible list of rational zeros. At this point, let's try synthetic division. Alright, so synthetic division is going to answer the question, is this a zero of the polynomial? You could also plug that into the function if you desired and see if you get 0. That's another choice. So let's try the zeros 1. Well, I need my coefficients, 5, 8, negative 9, and 2. So then my synthetic division, bring down the 5. 1 times 5 is 5. Add down is 13. Multiply, that's 13. Add down is positive 4. 1 times 4 is 4. It adds down, it gives us 6. Since the remainder is not 0, I know that 1 is not a possible rational zero. What about negative 1? Alright, let's try negative 1. Negative 1 times 5 is negative 5. Add down, I get 3. Negative 1 times 3 is negative 3. Add down, I get negative 12. Negative 1 times negative 12 is positive 12. Add down, that's not 0. That is also not a 0 because we do have a remainder. So negative 1 and positive 1 are both out. To save time, I'm going to jump around and I'm going to try 2/5. So bring down the 5. 2/5 times 5 is going to be 2. Add down. 8 plus 2 is 10. 2/5 times 10 leaves me with 4. Add down, that's -5. 2/5 times -5 is -2. Add down, the remainder is 0. So that tells us specifically that 2/5 is a 0 to the polynomial, specifically positive 2/5. Now, synthetic division with a fraction is a little strange, and so we have to be careful here, because it's true that 2/5 is a 0, but the binomial that gives us is actually going to be 5x minus 2. And so I know that this thing will actually factor as 5x minus 2 times some stuff. Now, if division works out, it should have to do with this and the polynomial that this stuff gives us. But we have to be careful because of this fraction. What you're going to have to do is you're going to take this denominator and divide each one of these things by 5. So 5 divided by the denominator 5 is 1. 10 divided by the denominator 5 is 2. -5 divided by the denominator 5 is -1. Then I know that this actually gives us the quotient x squared plus 2x minus 1. And so this is then 5x minus 2 times x squared plus 2x minus 1. And that equals 0. But now, since I'm trying to find all the real solutions, I'd like to factor this, but it won't factor, so I'm just going to use the quadratic formula. That is, x is equal to -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. This then gives me -2 plus or minus the square root of 4 plus 4 divided by 2. That's going to give me -2 plus or minus root 8 divided by 2, which is really -2 plus or minus 2 root 2 all over 2. That will reduce to give us -1 plus or minus root 2. All of my real solutions are 2/5 and -1 plus root 2 and -1 minus root 2. These are all of my real solutions. Now, for the sake of this, let's just make sure we realize how this could be written completely as factors. And so this could be written as 5x minus 2 times x minus the zeros, -1 plus root 2 times x minus the other 0, -1 minus root 2. And so if we needed a completely factored form, there's that. But notice that if we were just looking for all of our zeros are here. And these are all of our real solutions. So let's find all of our zeros again. Factors of the constant are 1, 2, 3, 4, 6, 12. All over the factors of the leading coefficient, which is 1. Oh, happy day. That means that all of our possible rationals are nice whole numbers. So our possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. So those are all the possible rational zeros. So at this point, let's do some synthetic division and figure out which one of these actually are zeros. So synthetic division, 4, 3, 2, 1, 0. So that's 1, 2, -7, -8, and 12. So how about I choose positive 1? Sounds like a good place to start. 1. So bring down our coefficient. 1. 1 times 1 is 1. To add down, 3. 3 times 1 is 3. Add down, that's -4. Multiply, that's -4. Add down, that's -12. Multiply, that's -12. Add down, that's 0. So our zeros, we now know x is equal to 1 is a 0. Great. Now a couple things, since we do need to factor this, let's go ahead and put it in our nice form. This is then going to be x minus 1 times, this was a 4th degree polynomial, so this one's going to be x cubed, so that's 1 times x cubed plus 3x squared minus 4x minus 12. So we're getting closer to our factors. Now the reason that I've written it like this is twofold. I do have to factor it, but at this point you could actually save some time. Notice that these will factor nicely by grouping, and any of our old methods that work, use them. Save yourself some time. So this is then going to be x minus 1 times x squared times x plus 3 times minus 4 times x plus 3, which then factors completely as x minus 1 times x squared minus 4 times x plus 3. I said factored completely and I'm wrong, because this will factor further as x minus 1 times x plus 2 x minus 2. That's a difference of squares, times x plus 3. Now the beauty of this is that now we've found the factored form of f of x. That is x minus 1, x plus 2, x minus 2, and x plus 3. But we've also found all of our zeros. Now if you wanted to use synthetic division to double check yourself, but I claim our zeros are 1, negative 2, 2, and negative 3. So here are our zeros, and here is the factored form. And if you wanted to do more synthetic division to keep breaking it down further like we did, you could do it that way as well. The intermediate value theorem, that is, let p be a polynomial function with real coefficients. The real coefficients are a necessary part. And then if we know that we pick two values, a and b, and those two values are different, and then you plug a into the polynomial and you get a value, p of a. And then you plug b into the polynomial and you get a value, p of b. And let's say that those two things are of opposite sign. P of a is positive, p of b is negative, or vice versa, your call. What can we claim about the polynomial? Well, I can guarantee that that function has to cross the x-axis between those two values. Now this is all because polynomial functions are continuous with no jumps, gaps, breaks, or holes. And then the deal is that when you plug in values into a function, if one's positive and then the next one's negative, you had to cross the x-axis if you can't pick your pen up. And that's what the intermediate value theorem tells us. It just guarantees that real zeros exist somewhere between two other values. One more note is that if you try this stuff and you get p of a and p of b having the same sign, then the intermediate value theorem just doesn't work here at all. You can't say anything. So just watch out for that. So we're going to use the intermediate value theorem to determine if the function has a real zero in the given interval. And the easiest way to do this is just pick the endpoints they give us and plug them into the function. So f of negative 4. Well, f of negative 4 is really negative 4 quantity cubed plus negative 4 quantity squared minus 6 times negative 4. I get that that is negative 24. Now let's use the other endpoint, f of negative 2. And let's plug it in. We get negative 2 quantity cubed plus negative 2 squared minus 6 times negative 2. I claim we get positive 8. And so we want to know, does there exist a real zero in the given interval? Alright, so what did we do? We found an a, we found a b, we plugged them in, we found f of a, and we found f of b, and notice that their signs are different. So because their signs are different, I can say that yes, by the intermediate value theorem, there must exist some real zero between negative 4 and negative 2. I don't know what it is. Maybe I can find it. Maybe it's hard to find. But I guarantee that it exists. So let's try it again. The intermediate value theorem, we want to determine if the function has a real zero in the given interval. So let's just play the game again. Plug in the endpoints. F of negative 5, that's going to be 5 times negative 5 quantity squared minus 5 times negative 5 minus 8. I claim that that gives me 142. Then let's find f of negative 1. That's 5 times negative 1 quantity squared minus 5 times negative 1 minus 8. I claim that should give us positive 2. We want to determine if the function has a real zero in the given interval. And the answer is not no here. The answer is, I don't know. I can't determine. That's all I can say. And that's really because the intermediate value theorem only actually applies if you get different signs when you plug in two values off the x-axis. And so anytime you get the same sign, the answer is, I don't know. And that's the best you can do using the intermediate value theorem.